Good afternoon, everyone. So, we are here today, the second session of our astronomy code camp. And today we are going to look at some simplified context in which we are going to look at radio pulsar data. And so, many of you must be well aware of what are radio pulsars, but just to explosion when massive stars finish their nuclear fuel, and at the centers of these explosions, the outer envelope has been thrown out in these explosion, and there is the inner core which is contracting and so on, and this contracted core may turn into a neutron star which may manifest itself as a radio pulsar. So a rapidly spinning star which is about maybe 10 kilometers in radius, but mass of the sun is inside that, and it is very rapidly rotating. 1 second or even much slower, sometimes milliseconds, is the rate at which it is spinning like this. And there are beams of radiation coming out from the magnetic polar regions. And actually, let me just try to shift to one of the visualizations which might help us. So that's the star, and that's the spin axis, and this is the magnetic axis. It may be different from the spin axis. So as the star rotates, the magnetic polar regions, kind of like a lighthouse, it may come and flash towards you. It may not, then it will not be a pulsar. But when it comes and flashes towards you, it may manifest itself as a radio pulsar. And the first discovery was by Jocelyn Bell, working with her thesis supervisor, Anthony Hewish, and at Jodrell Bank. She found that when she was looking for some kind of interplanetary scintillations, they are called, like the twinkling of the light that we see. So these radio scintillations, and she was studying, she found some peculiarity of data, which was then identified later. Of course, initially people did kind of wonder whether it may have had been aliens, little green men sending out those pulses of radiation. But very soon it was deduced that these are the kind of objects that we are now very familiar with, relatively well familiar with, those neutron stars which are manifesting themselves as radio pulsars. And you may see pulse to pulse. For instance, there was a musical video which was also, this was the cover for the very first pulsar, 1919 plus 21, I think that's the name of this pulsar. So what does the name convey? That also maybe very quickly I will just try to mention. But if you try and average out the information that is coming from it, folding it within the period of the pulsar, you may find something like this, which is like here, I mean, with time, or like you take the rotation of the pulsar and make it 360 degrees. So you may have that on this axis, and if you have intensity kind of observations, you may see a profile of this kind. So this is the kind of information we are going to look at today. So for this kind of information, there are these very useful tools called Stokes parameters, and which are in intensity units. I, Q, U, V are the 4 Stokes parameters, and by combining them in various ways, you will know everything about the intensity and the polarization state of any radiation that is coming towards you. And the radio pulsar the radiation is generally very highly polarized, though we may find some pulsars which are not so polarized, and these are high magnetic field objects, so that that connects well. And so that's about it, except for so what is the I just wanted to put these objects in context for you, because today this is what we are going to be looking at, and we are going to do this in 2 segments. The first segment, we are going to go and look up online data, which will be giving you these Stokes parameters. In fact, I'm just trying to check. Yeah, I think if I share that, I can tell you what I wanted to show. I think you can see this, right? You can see this in my screen share. This is one database. This is called the European Pulsar Network database, and it gives you a host of pulsars and their average profile data. So you click on any one pulsar, and then it will give you the images will show you what kind of data is there. So if you see the blue, orange, green lines, it means the polarization data is there. If you see only the blue line somewhere, sometimes only the intensity information is there. Only intensity information, and then this one will give you the data itself. And I'll not say much about this, but this is what we are going to use today. And using this, we are going to, for the first part. Yesterday, all of you were there. Amritanshu put you into the picture how you can just pick up maybe data and plot it, and how to do plots and so on. We'll go further in it. So the first part is just very simple. You have this data, you plot it, and understanding what Stokes parameters mean and how they are going to give you the polarization. The second part is going to be getting such data through FITS format, which is the standard format. And our speaker for today, whom I'm going to call in now, uh, Aniket Prasad from NIT. Agartala, right? So Aniket is going to take us through this, and our speaker from yesterday, Amrutanshu, is also with us. He's going to help any questions, queries you have. He is going to help us from the background. And Aniket, I should hand over to you with your screen share and so on. Your screen share is in the studio, so whenever you are ready, we will have it. And so I should hand it over to you, right, Aniket?
Okay, thank you, ma'am.
One thing probably I did not mention, and I think are you going to? Amritanshu promised to talk about that also. Basically, the names of the pulsars that we had, they are given by some numbers, and those numbers are their coordinates in some kind of equatorial framework. And Amritanshu will help you understand that a little more. You will see these numbers flash by quite a bit. So I'll hand over to you, Aniket.
Thank you so much, ma'am. I will take over from now.
Your
Hello, guys.
visible. Your screen share is visible, and you are audible.
Okay, thank you, ma'am. So, hello, guys. As ma'am today said, we will see how pulsar data is handled and how do we plot pulsar data. I am sure you might have seen those pulsar profiles very frequently. These are like some spikes and then normal signals. So we will see how to plot those data using Python. As I am told, you have been introduced to Python as a language and know the basics of it. So I will just move forward with how to plot these data and how to read these data. So this is one of the notebooks I will be using today to plot a pulsar data from the EPN network, which ma'am just mentioned. So first of all, you should know that Python is very preferred language because of its vast number of modules and libraries, right? So one of the major libraries which we actually use a lot in astronomy is AstroPy, which I will be using today. And today, and I think you should know about that library. Also, if you are going to work in the field of astronomy, there are some basic libraries which you should be knowing or you should have heard of, because these are mostly used, such as AstroPy and some others I will mention as we go along. Okay. So this is just an introduction how to install these libraries, because these libraries are not coming preloaded with Python. You have installed Python in your system, but you cannot just use AstroPy by calling its method. You have to first install it. I'm sure you have done this. So this is just a basic thing. You can just use this command, that is pip install AstroPy in your system. uh, it is in Windows. I mean, it you have to have pip for that. So if you have command line, you just type this pip install AstroPy, and it installs AstroPy along with all its functions.
Uh,
Uh,
pa- uh,
you
Aniket, I just wanted to check once with you. that this, if you are working in Google Colab,
Yes,
most, I
ma'am.
mean, all of them are doing that. So very few may be actually having this installed in their system and so on. But so they, whatever the instructions you are giving are according to Google Colab, right?
Ma'am, I was mentioning that this is for system, and another thing is that if you are using Google Colab, you just need not to install anything. You just call it and then use it. That's it.
Yeah.
These
Sorry,
things
sorry.
are already installed in Google Colab.
Please go ahead.
Okay, sure, ma'am. As ma'am again mentioned, in the Google Colab, these things are already installed. You can see that disk space. There are much is already being used. This is all these things installed already for you. So you just need to go and use it. Okay. So moving on, as I said, you should know these libraries for you. This will be beneficial. Like AstroPy, as I said, this is the basis for astronomy. SciPy, this is another scientific library. You might come uh, its use in some way. And then these are NumPy array, NumPy library, which is very, very beneficial to handle arrays and data as such. And these two, Matplotlib and Seaborn, is what we will be using for plotting. So today I will be showing the Matplotlib method to plot this pulsar profile. Okay. So as ma'am mentioned, we will be using the European Pulsar Network data. So we already know what is this database, right? It has 1,719, 79 pulsars in its catalog, but there are more profiles. Like same pulsar has been observed by many scientists in many different energy profiles. So therefore, the profiles are more than the number of pulsars. Okay, it doesn't matter. We will use one of those for plotting today. Uh, you can see the database if you want, as ma'am has shown. This is the database, and you can just click and just access any profile. Okay, so if we move forward, I am told you have known data fetching, so I will not go into that, and it's basically Python comes with loaded functions for that. But as I mentioned, today I will be using AstroPy. So I will teach, show you how to read ASCII files or any files using AstroPy. As ma'am mentioned, and as you can see on the database, these are ASCII profiles, right? So ASCII profiles are basically text files. These are text files, just written some text. Okay. So if you have to read that text file, AstroPy gives you a function that's creatively named ASCII. So this is a module which is astropy.io import ASCII. In this way, this is the library that AstroPy, and this is its module which we'll be using today. That is ASCII. Okay. So another thing in Google Colab, you can, Shift plus Enter runs your module, cell, and jumps to the next cell. So don't mind that if I jump so quickly from one cell to another. So ASCII has a method that is dot read method. It is what actually enables us to read ASCII data or any kind of tabular data from text files. So you might have seen CSV type files, which are like comma separated formats, and then some files like these data, simple tabular data, but in text files. So all these things can be read the read using the read function, and read functions has some flexibility with its source. Like if you are using this, how will you download one data from that? So if I am choosing this profile, let me choose one. Okay, I am choosing B1910 actually, 1929 plus 10. So if you search for this pulsar in this database, you will get the ASCII profile, and you can just copy this link. This is the link to this file, this data file. Okay. So now you have might have known we can just declare variable like this in Python. So I have just copied that URL in a variable named URL. Okay. So while reading that data, so I am using a variable again, PSR1, that's my short for pulsar1. So using this ASCII.read, it requires two, at most, at least two or one parameters, but the foremost is this source URL. So this parameter, this is a basically a function, right? The dot read function. So it has parameters. First of them is the source. This source parameter requires the name of the file or the path of the file or even the raw file to read. As I have mentioned, this URL, this parameter can be replaced by either a name of a file, as I mentioned, like there is some file dot abc.txt. So you can write abc.txt, and if that file exists in your directory, it will read it. Now, it can also have simple table separated data, like if you have some arrays, like there is a list, let's say var is equal to some data, okay, 1 comma 2 comma 3 and 34, and then another something like that, some data. That data can also be feed into this source URL, and this method will try to parse that data, try to read that data to understand if that is any ASCII file, and if it is, it will show that data. Also, one major advantage of using Google Colab is this: if you hover around any function, it will tell you what that function is and what does it return. So that is also very helpful in Google Colab. So here what I have done is I have transferred this URL which I want to read. This is the this one is an example for J0006 plus 1834. This is from one of the original pulsar observations of 1995. So that's pretty old, but I will use that for now. So this is the URL to that data, and another moving on to the next parameter of this data. As I have shown you the file, you can see this file. No, not this one is not actually that file. Let's move to that file which I am actually plotting right now. So this is the data which I am actually plotting right now. Okay. So you can see there is total power only, that is looks like a heading or a comment for the data file, and it has two, looks to be two columns, right? Time and data. There is no Stokes parameter mentioned in this observation. Okay. This one is the simplest data you can find for plotting. So here I have used names is equal to time and data. Names is a parameter which actually helps you to define the columns of your data. Like if you know this ASCII.read is going to some source which has a tabular data. Like we know that this data is tabular. Like I'm sorry again. This data is tabular. Time and then some data, time and then some data. So we know that it is tabular. So we can name its columns. Now you might be wondering why am I not using these as columns, right? So ASCII has one, you can say a problem, but I won't. But I will show you. For now, this is names is used for naming the columns of the data. If we don't use it, okay, let me just erase this parameter for now, and let's try to run with this. Like this is URL. Okay, let's completely erase all these parameters. Let's just try to run with URL only. So you see this is getting an error, and it looks pretty long error, right? So this is what happens if the ASCII.read method cannot read your data file. So I passed an URL and it tried to read that data, but it cannot read that data. So it gave an error. It tried a lot of various patterns, various file systems, but it cannot read that data. Okay. So this is what the error key is, that is inconsistent table error. It cannot identify that table. So that's why without any further information, ASCII.read is failing to read my data. So for that, what I will do is, I mean, we'll give another parameters which we know about the data. Like we know that there are two columns. By seeing the data, we can know there are two columns, time and data. So we can mention that and help our ASCII.read method to read the data. But again, let's just involve name parameter and remove this data dot, I mean data start. Okay, and let's try to run again. Do we have success in reading the data? No, again it fails. Now you might be wondering, I have given the URL, I have given that these are two columns mentioned in the data, and still it's not reading the file. Why? So the answer to is like any file system, when ASCII.read starts reading, it started from here, it started interpreting the file. So first line it got total power only. So it understood, okay, there is a string of data and then there is next line. But in next line, it never gets that same pattern again. You can see the after that column total power only, there's a space and then there is two spaces. So the interpreter is not getting the same pattern again. So it cannot identify if this is a table or not. So that's why what I will do is I will mention from where the data actually starts. Okay, this is data start is equal to 2. I will explain why that. Now data exactly in this file, data is this, time and data. This whole thing is our data, right? These two are not actually part of the actual data which we will be requiring. So what I did, I told the ASCII.read method that my data starts from 2. 2 is what? This is the first line. Any programming language has indexing always. I mean, most of them has from 0. So first line is always like index 0. So the interpreter came here and it understood that, okay, this is 0th line. This is the first line. And I have to ignore that because why? Because my command says data starts at 2. So data started at 2. So it started reading data from 2. Now in 2, it detects a pattern. What is that pattern? Okay, there are three spaces, some float data, I mean number data, then some space, then some data. So it started detecting this pattern. Okay. So now ASCII.read will be able to detect that pattern and will be able to detect that table. So let's run that. Did it detect the table? Oh yes, I guess it is detecting the table, is it? So how to check is it is detecting the table or not? Let's just run this. Uh, okay, there is no error. So this is actually detecting the table. I mean, this has successfully executed. So if we want to check what are the columns or what are the data, okay. So we can just call this variable which I just made PSR1, and let's just start typing call names. This is a I mean parameter of PSR1. I mean this variable ASCII.read returns a table, and this call names helps us to read the columns of those tables. As I have given on already given these names is equal to time and data. So the PSR1 call names, that is the column name, will always be my time and data. If I change these, let's just say you have understood that this file can read the data if I just fill in that data starts at 2. So the pattern it can detect. Now let's try without names. Okay, what will happen? So it again successfully run. But now if we check the psr1.call names, it is giving its own column names, column 1 and column 2. Why this happens? This happens because it's I mean it read the data and it didn't find any column names. So what it did, it inserted its own column names, generically named call 1 and call 2 for those columns. This is what happens if I don't mention any parameters for names. Now, if I mention these parameters, time and data, it will start detecting the data and it will find that, okay, there are two columns and I have two parameters. What are they? They are time and data. So they will start, I mean, the ASCII.read will automatically name those columns time and data. So if I do this, I mean, let's just run this once again. If I do enter the names parameter, then if I call psr1.call names, the column names will be time and data. This is what actual function of names is. This is mentioning what are my column names. Okay, so we have successfully read the data to our Python script, or should I say the notebook. So we have the data. Now this is PSR1, that is this is the file which is actually containing this table format returned from ASCII.read. So what if I just call this PSR1? This is equivalent to printing PSR1. Okay. So this is telling me all the info about table. So my table, which this file read, was length 512. So that means the number of time and data profiles given here is 512 in all. Okay. And this was my column name, as I said. And this is the data type. This is part of the pattern it detects. Like uh, when it started reading these numbers, it detected the pattern that these columns are all string type, I mean integer type, float types actually, decimal points. Okay, so it read that float 64 is its data type. So it completely read that data. This is the complete data. Now you are wondering how to access this data, right? So if you move to the next cell, as I have shown you, it is very much compliant with the indexing of Python. I'm sure you know the indexing, that is 0, 1, 2. These are the indexes of any array or vector of the data, right? So lists, tuples, everything obeys this indexing. And it is also the case with this ASCII.read table file. So if you want to access any particular row, let's just remove this and I will show you. Let's just access this PSR 0. 0 is what? 0th index. Okay. So what will it return? It will return the first row. If you can see the whole data, that is the table we accessed. This happens to be the first row, right? So if we just use PSR10, it will return that first row. Now, if it also actually obeys that reverse indexing, you know, reverse indexing, like if you want to access data from the last position, the last position is numbered -1. So it will also obey that -1 thing, that type of indexing. So if I print PSR1 -1, that is the file's last index. So last index is this, right? This is the very last entry in the index, in the table. So it will return that table. Also, you can also see that it PSR1, that is table file, can also print indexes like this. That is the slice of the index. I mean slice of the file. So this, in this way you can access each data and visualize each data, right? Also, you can see that there are two columns. So how to access data from any one column or any other column? So I have two columns, data and time. I have just named them, right? Time and data. So here, if you write like this, this is what the table is actually what? Row into column, right? Any table is row into column. But I mean column into row. What should I say? Yeah, column. Let's just say row into column. But while calling this PSR1 data -1, what is this doing is we are accessing one of the columns, and we are accessing the -1th element of that column. Okay, so if we try this and try to print this, this will print the very last data. This one is the last data, I mean the entry in the data column. This one is the last. This was accessed to -1. So we can see it is accessing that -1. If we go -5 maybe, it will give us the fifth last data. How should I say? This one should be 1, 2, 3, 4. This one should be the fifth last data, right? So this one will be printed if we do data -1. We can also change this. We can go like time, maybe time -5. That will give us the time column's fifth last data. So this is all how you can access these data and play around with it. Like you can just pull out any part of that table as a data, like I did. I just pulled out PSR1's 0 to 3rd index, and it just pulled me out this result, right? So this was all about I mean accessing the data, understanding the data, and reading the data. So now if we jump to how to plot these data, right? So for plotting, as I previously mentioned, I will be using matplotlib. It is a Python library which is very widely used for any kind of plotting. Mostly all of the plotting functions are available here. Like you can plot line graphs, you can plot bar charts, anything from this module. I will highly recommend if you can just go and read its documentations or its tutorials or examples. That will be very helpful to understand fully what all functions it can, serve. So again, the installation, if anyone is in system, is similar. Pip install matplotlib and that will install. So for plotting right now, plotting today, I will be using matplotlib.pyplot module. Okay, this pyplot module is actually the interface of matplotlib. What I don't think interface will be right. This is the module which accesses all other functions of the matplotlib. So it is just a convention to introduce it as PLT, import matplotlib.pyplot as PLT. You can name
And
anything.
Aniket, when you were discussing about installing, there was a request whether it could be discussed for Mac OS also. You could perhaps do that at the end or now, as per your convenience, if you would
Ma'am,
like
I
to take
will,
that up. For now, yeah, proceed with the collab.
yes, ma'am, I will proceed with the collab. I will address his problem
Yeah, at
specifically
the
at the
end.
last. Okay. Okay, noted that you have installation problems also. I will do that later. For now, in Google Colab, you can just import as I mentioned. This is also already installed for you. So just import this as PLT. As I was saying, this is just a convention. You can use any name, but PLT is very famous. Probably if you search PLT in Python in Google, first result will be matplotlib. In the second line, what I have used is called something called magic function. This is collab, notebook specific, more like it's a concept of IPython. So this helps you to embed those matplotlib graphs in your notebook. So need not to worry about why this is used or what is this its function. You can just understand that it is helpful in embedding those graphs. Okay, it will be very much understandable if you just read about it. Okay, nothing much there to explain. So now moving on to our main agenda, that is plotting a pulse profile. As I mentioned, I will be using matplotlib and I will show you how to plot anything from matplotlib. So as I have already imported pyplot as PLT, so you can use that PLT as a name for calling any of the functions of pyplot. So basically for plotting you just need this line, right? This line, plt dot plot is the what is what actually gives you a graph like shape, and it takes some parameters. What are those parameters? First one is the x-axis data and second one is the y-axis data. Okay, so this x-axis data can again be entered in any way, like you have any array, any list, any kind of, even like a collection of any numbers, any iterables, you can feed in here, right? So what I am entering here is PSR1 time. What is PSR1 time? As I mentioned, our data has two columns, time and data. So what do you think if I just, if instead of PSR1 time minus 5, I just call PSR1 time? Yes, exactly. It will call my that column. Okay, as you can see, it is column and it has all those data. How do you know it is that all the data? You can check from PSR1 time dot check its length, which is actually given here 512. So you are sure that PSR1 time gives you all those data. So when you are plotting any pulsar profile, what do you exactly need is, as the data also mentions, it is what it is, time and power, maybe time, and it is total power only, integrated profile. So time and data. So when we plot any pulsar profiles, we choose plot, what actually is that we choose x-axis as our time axis, and we choose y-axis as our data, as our intensity. So what we have read in this file is two columns, time and data, and we want to plot it. So any plot needs a dependent variable and independent variable. So for me in this file, time is that independent variable, the x-axis, and data is my dependent variable, that is y-axis. So of course, if I have data like that, there might be some, plotting possible. So we will achieve that using matplotlib here. So as I was saying, this is the main line to plot it. So you can just plot without this also, like this. Plt.plot, just the x-axis data and the y-axis data, right? What I used here is, as you might have seen, this R. So this is nothing but this is the color of the plot. You can call it like this also, color is equal to R. R is the code for red. You can use the B or G or anything like that. There are codes which are available in the documentation. For now, let's use R. Okay. As I said, even without, these are codes actually, the color codes are. So even without mentioning that it is color, it will detect that it is R is talking about color only. For beginners, you can also just like see this color is equal to R. That is also a very fine way to do that. So if we go from here, like go to the complete plots, how to do it. So let's just walk through it. So plt.figure, this function actually helps you to decide the figure. Any graph in matplotlib has two functions. Two major components. One is this axis, which has the data, and another is this figure, this complete, what we say, graph, this figure. So because this is what actually renders all those data inside it, right? So this plt.figure helps me to decide the size of this graph. So this, instead of this 8 into 8, if I just take it something smaller, 4 comma 4, you can see the graph size has just decreased very much, right? This will help in various cases, like if your data is very, congested and you want to see exact variations. So you can check with different figure sizes. The standard is 8 comma 8 that I will be using right now, so that I can also show you the variation from this graph. Okay. So this was the function of fig size. This is a parameter. Parameter of this method, and it takes values like a list. A tuple, two values, x comma y dimensions. It can take that like that. There are various other ways to decide the figure size. I will recommend to just check on these some of the tutorials. They will show different methods to achieve this, but for me this is the simplest one you can do right at the plotting time. So moving on to the next function, this is plt.grid. So of course this helps you to draw grids in your graph, like a physical graph. If you have seen, if you don't use this, this will basically be a plain plot, which is also very fine and looks good too. I just needed to ensure that you see the function of plt.grid. So without plt.grid also, this is a very good plotting. So we can either use it or not use it. It doesn't matter. But I wanted to show you that it is also one of the functionalities of matplotlib. So moving on to the next function, this is plt.title. So as I mentioned, plt is everything for the graph. This function, this module has everything, every functionality, every manipulation of the graph. Okay. So plt.title helps you change the title of the title of the plot. As I have written pulse profile, this is actually rendering here above the actual graph. So if we change something from this, it can go to various other values. Again, this takes a string. So in declare a string previously and just enter this. Like for example, you can do this. Let's just say we have a pulsar name. Okay, we have a pulse I mean name, and let's just give it a value. So we can also do this. Just give it a string value. So what will happen? The string value can be rendered as a title. Okay, so that's what helps in. I mean, if there are too many graphs, you definitely need titles to understand what are all these. As I already mentioned, plt.plot is helping us to get the data and actual plotting. This manipulation is done with plot. There is another function which you can use, like this is plot is specific for this line plot. Okay, you can use scatter, that is another form of graphing. As you can see, Google Colab also suggests scatter, plt.scatter. This is again why Google Colab is so helpful. So if we do plt.scatter, it will render a scatter plot. This is a scatter plot. Okay, so this function here defines how to render this data. Is it plt.scatter? There are other functions for histograms and bar charts and things like that. Those are other functions which you can definitely check. But for now, I will stick to the line plot because that is what mostly used for these types of continuous data. So moving on to the next command, that is plt.xlabel. So x label and y label are helpful to determine what are these axes. This thing, I mean time and this pulse data, these texts can be rendered using x label and y label. And it also has other parameters like font size, which defines how much larger this text should be. This parameter is also there in plt.title, so need not to worry about if the title looks small or something. So these x label and y label are for that. X label for x-axis, y label for y-axis. Again, as I said, hovering over a method will help you. I mean, it will show you this pop-up by Google Colab. It also helps you to understand what kind of parameters are there in this. Like you can see, X label has a string parameter, that is my data, actual thing to, I mean, text to display. And it has other parameters also, scalar, optional, and these things, which helps you to like play more with that data. So for now, I am providing the minimum for label, that is what text to appear there, that is time and then pulse data. Okay. So moving on to the next, this is plt.legend. Legend is, as you might know, any graph has a box, a legend of what that graph is explaining and what all those things mean. Actually, this is just a single profile, so legend is not very much. I mean, does not appear to be very much useful here. But I just wanted to show you, like this can be helpful in mentioning what are all those graphs. I will come to when we will be plotting multiple graphs in the same plot. This will come in handy. So plt.show is the, I mean, not very much required, but it is a good practice because backend of matplotlib is a bit intensive, but in Google Colab doesn't matter that much. So even without plt.show, plt.close, these are some functions I will explain. Even for now, plt.show, let's just assume that plt.show helps us to render this graph very, I mean, conveniently in our notebook. Okay, so what we have done right now, let's get a quick recap. We've defined a figure with its size, then defined a title for the graph, pulse profile. Then we defined what data should be plotted, and then we defined what color should be that of graph. Okay, that plot. Then we defined what should be my labels, what should be like visible to the user, what are these labels, and then legend. And if combining all this, when I run this, you will see a plot. What is this plot? This x-axis is, as I mentioned, PSR1 time, and y-axis is PSR1 data. This is the time axis, and you can see the maximum value is around 0.7. uh, I think we have the data, right? Yeah, see, the last value of time axis is 0.6937 something seconds. Okay, so you can ensure that this is definitely the x-axis and it is ending at that point, like 0.69 and something. Okay, so this is how you plot a very simple data. Mind you, this pulsar data was very simple. Like it is just data, I mean time and integrated profile. This has to be the simplest one to plot anything. Okay. So from this, I wanted to tell you how to plot a graph using data for x axis, data for y axis, and stuff. So now we will enter take another profile, and this time this profile will have Stokes parameter, which is the norm with these data. Like when we observe pulsars, we actually document this IQ UV parameters for that. Okay, perhaps ma'am would be very, I mean, ma'am would explain these parameters more from the point of physics, but for now you can just understand this, that this is what exactly, I mean, helps in visualization of polarization of pulsars. So if there are, you come up across a data from the network, I mean database, where there is Stokes IQ UV written and there is time and data, but this time data has four columns and time has again that one column. So that means this data is depicting these four parameters, right?
Aniket, at this stage, probably, I mean, it would be useful just to mention that like these four are in intensity kind of parameters, and
Yeah.
these are the standard way that we are defining polarization. I is the total intensity, and the QUV are giving us the total polarization. So if we are looking at linear polarization, which is that the radiation is coming towards you, and in the perpendicular plane, it is constrained to kind of the electric magnetic field vectors along a line for a linear kind of polarization. So that we would L is our this Q U V. V is giving us the circular, and Q and U are giving us the linear polarization. Here the definitions. You are going to do all of this, Aniket. I'm sorry. If you are going to do all of
No,
this, I won't. Please
no,
go
ma'am.
ahead.
I
Please
was
go ahead.
just demonstrating if that helps for you.
So you show
Like
it
I
then.
just
Show it then.
mentioned it
Then just
that.
no. You show that graph. We will just mention it. So we have the Q and U Stokes parameters are going to give us a linear polarization. U. Hey, यहाँ पे थोड़ा सा कुछ problem लग रहा है. U V is our circular polarization. Q and U will give us linear polarization and a kind of a reference angle with respect to the linear polarization in this plane, like where plane of a tangent to the sky. On that, if it is constrained to oscillate along any one specific direction, there will be a reference angle with which defines which is the direction. So that will be defined tan inverse. यहाँ पे है वो फॉर्म थोड़ा नीचे जाना
No, ma'am.
अनिकेत.
I haven't mentioned that. I just
अच्छा अच्छा.
referenced
हाँ हाँ हाँ.
that these are the
हाँ हाँ.
parameters.
ठीक है. So that the tan inverse U by Q, that will also be. So there are, when you look at the graphs, we are going to then see I and L which is given here, and V which will be there, and niche in another graph, usually this is the standard way they are plotted. The
So
position angle is also given. There it is. That is the position angle. So this is drawn usually in a separate box at the bottom. So even if we are not doing it right now, we can do it as a kind of a exercise later on. And one thing is that these V and our position angle, when the data is very noisy, they will keep going haywire. And I think Aniket has also an exercise where he is going to show how to select that only where we have sufficient polarization and so on. So sorry, Aniket, you go ahead.
okay. Yeah, I will demonstrate how this polarization angle is also plotted, and you will see some patterns. But again, if the data is very noisy, there is very less scope of pattern. But I will show you. So for now, you just understand that these IQ UV parameters are what determining our polarization intensities, right? These are not exactly polarization intensities, but these are the parameters to manifest that I mean, as a observable data. Okay, so this has been done by scientists they have separated the data for us. So this time I am choosing this pulsar B1929 plus 10 at 1.408 gigahertz. You can find that data again in this, and probably this is that data, B1920, 1929 plus 10. So let's try to plot this. So what is the major difference from the previous one? Previous one has just two columns, time and data, X and Y, pretty simple, right? But now there are more than two columns. There are actually five columns. So we need to account for that, and we need to plot, I mean, maybe first and second column, then first and third column, maybe first and second, third, fourth in same plots. So I will show you that how to do that. Okay. So as I mentioned, this time I am using B1929 plus 10 pulsar, and this data has IQ UV parameters to demonstrate. So I will be using that. Again, we have gone through this URL of that data taken from the database, declaring a pulse, I mean variable, and calling ASCII.read again. URL, that is the source, then names. This time, giving two or three columns won't work. Why? Because if I just tell my ASCII.read, there are only two columns. Let's just do that. There are only two columns, and that data starts at 2. So again, it will understand that okay, data is starting at 2. I will start detecting pattern from there. But when it goes to its parameters, it has only 2. Then it will get confused. Okay, my data started at 2, but this time I cannot decide there are only two columns. What I am finding is five columns, but my user is telling me that there are two columns. So this is not, I mean, it will confuse the interpreter. So if we do this, it will not actually run. It will throw an error. Error is again that only that it cannot read the table. This is the actual error message. Unable to guess table format with the guesses listed above. Guesses listed above is actually what my parameters, extra parameters. These are my guesses. Like I am guessing that file has to have, we had what, five, has to have five columns. This is my guess. If my guess goes wrong, which was in this case, that my guess was that there are two columns, but it was not. So it threw an error. So that's how you manipulate according to your data, because see, you can ignore this, then again you will again be able to like read the data. It will start detecting pattern, because you can see that from the second index the data is very much tabular. Like there is some integer, I mean number, float, space, float, there is a pattern. So this interpreter is smart enough to detect that, but it won't be what we say. Yeah, it will be helpful, doesn't matter. But by mentioning my guesses that there are these five columns, it will help it reading and also help me name those columns, right? So I am actually essentially naming those columns here. If we don't mention it, it goes call 1, call 2, call 3, and so on. So by names, again I am mentioning that these has to be my column names. So again, if I call psr2 dot call names, again you can see psr2 dot call name gives me time, iq, uv. That is my parameter for column names, right? Again, psr2, if we call that data, once think I should mention this, that always while coding anything, always play with your data and play with your file. Always know what that data is, right? There was no actual need of calling PSR2 here, but I just called it. Why? I wanted to see what is actually my data. My table length is 491 this time. Previously it was 512 or something. This time it's changed. If I hadn't called this, I wouldn't have known. So always try to visualize what is your data, right? And also again you can see these are the data types columns, and this is the actual table, the actual data. Uh, So as the ma'am also mentioned, and this is basically I will explain in the later notebook in detail. For now, as I said, Q and U will give you linear polarization, or yeah, as ma'am mentioned, Q and U will be giving you linear polarization. So this is actually the physical formula for getting linear polarization from Stokes parameter. I will not delve into that right now, but I will explain it. Don't be panicked, and don't be panicked from this cell also. This is import numpy as NP. As I mentioned, for any astronomer, astropy, scipy, numpy, matplotlib, and maybe pandas or seaborn. These are some of the libraries which you have to know. So this numpy is just a library to handle all kind of numbers, any kind of numbers, vectors, matrix, simple numbers, mean, median, anything it can handle. So this is again a very handy thing if you are doing some mathematics from Python or calculating something numerically. So I will let's just not get occupied with this. I will explain this. But for now, you have something IQ UV, and you know that some manipulation of Q and U columns will give you what we say linear polarization. Again, I think this should be mentioned. As I said before, that you can call individual columns PSR2, and let's say we get Q. Okay, PSR2Q. It will fetch you that column, right? So it also follows your mathematical operations. PSR2. Let's just add it. It's a simple operation, but it doesn't mean anything physically. PSRQ plus PSRU. It will add that data, right? It is actually adding that data. So you can do that. You can multiply. You can do PSR2Q times PSRQU. That thing also can be done. Okay, so why this will be helpful? Because if you have IQUV data, or I mean, it is formatted in this format, then you can plot circular polarization, linear polarization, and everything with some mathematical manipulation of these columns. So that's why I'm telling you that these columns can be mathematically operated. You can try that, and I will very much encourage you to try that. As is, if you ignore that NumPy is imported, so you can see that here basically it is np dot square. This is a function to square a number, square an array, number, anything. That's functionality of NumPy. But you can see what I am essentially doing. I am taking a column, I am squaring it. So you can see that the column has mathematical flexibility. It can square, it can square root, it can multiply. This thing I need you to remember, because that will be very healthy, I mean handy, when you are actually plotting these data. For I mean, as you have seen, scientists actually plot all the polarimetry data. So this thing helps you in doing that from Python. So again, previously, as I had mentioned, this is the same code copied again, just to show you that this time, if I do this PSR2 time and PSR2 I, what is I? I is my first column, if I am not wrong. Okay, second column. Time is first. This is second. Okay. So this second column, I is the actually the integrated intensity. I mean total intensity. So if we plot that, what we had previously done is PSR1 data. That is the only one column. But this time it is PSR2I, one of the four columns. Okay. So I can plot that. So if I plot that, then I will get the variation of I with time scale. That is the time axis. And you can see this pulse profile. Previously, in the previous pulsar, pulse profile was something different. Now, okay, now it looks a bit, I mean, steeper, and it's different. So I just wanted to show you that pulsar profiles are very much like different from each other, but there is a general pattern of this spike and then normal noise. So I'm sure you can visualize more of these pulsars using this simple thing, that is extracting that ASCII profile, then using PLT and using different data here, and just plot it. So you will see different eye profiles. I mean, if you plot eye or if you plot that data as a whole, you will see these pulse profiles. Now I'm showing you another thing, which is what you will see the use. Like most of the graphs where more than one or two plots are together, they are done using this use of subplots. Uh, as ma'am mentioned, we generally, what do we do is we plot a pulse profile, and then in a subsequent smaller plot we plot the position angle. So how do you achieve that? That could be done with the use of technique of subplots. Right now I will show you how to use the subplots, and I will explain you how to actually plot complete polarization uh, data for any pulsar, okay, later. So for now, let's just see. As I mentioned, we can just name a variable and use it as a title and something. So I have just named it. I will show you how to use it. The main thing to learn here is this use of plt.subplots. Now you have seen that here plt.figure, plt.title, these things assumes that you have one plot. That is, you have assumed this. I mean, compiler assumes you have one plot and you are plotting in that. But when I mentioned this line fig comma x, these are my variables. No need to worry, but these are conventionally used. So okay, plt.subplots. This subplots actually helps you render more than one plots in the same like what do you say? Same compilation. Like you can do this if you mention this command and then plt.show, and then you add another here plt.show. It will essentially what it will do, it will plot another graph, no problem, but it will basically be reference, I mean, overlaying that. This is something from backend of matplotlib. You just understand that using of subplot is more efficient if you want to plot more than one graph uh, with same compilations with same data. Then we use subplots, that is more convenient. So again, subplots has various parameters, and some of them which is like more of the requirement is these: the number of plots, this three. This is I mean, depicting how many plots I want here. Like my plt.subplot, how many plots it needs to render. As I again said, Google Colab helps me showing all the parameters by just hovering over it. So this is the actual function, I mean actual method subplots, and it has a lot of things, lot of parameters. It has n rows, n columns. These are like uh, n rows is number of rows of the plots. Like if you don't enter anything, that is by default there is one rows and one column, that is one plot. It will render one plot. Share x, this is a parameter which helps you share the axis. Like as I said, there are multiple plots for same compilation. So there are sometimes like you plot, what do we say, you have plotted something like a DC plot, and then its equivalent AC plot. We share that axis, right? We share the axis and we see the variations. So those things are very much required in science. So this function sharex helps in that. Sharex helps in sharing the x-axis, and sharey helps in sharing the y-axis. And there are various other I mean parameters, and there are actually a lot of parameters of subplots. Again, I will, I mean, recommend you to just go to the source or just go to the, I mean, documentation of matplotlib to read more. But you can also here, I mean, read more here also. Like there are a lot of things to understand, I mean, to explore, actually not understand, explore. You can check every functions and you can see what they do. For now, this is figure and this is axis. These two were what these two variables are taking is the figure component of the graph and the axis component of the graph. PLT subplot returns a figure component and an axis component according to the number of plots it requires to render. Okay, this fig size again, I think I should mention it. This fig size here is like the size again for the graph. size of the graph. Okay. Again, sizing has different methods, but this one is the simplest. So let's take the first of those subplots. Like fig has a figure and axis has the axis. Again, I said that figure just renders you a square or something like I mean a box, and axis renders you the data and plotting. So for as I mentioned, there are three subplots I am rendering here. So first of those subplots, this is the way to access those plots. You can do one, you can do two, but not three because there are only three and indexing starts from zero. So zero, one, two. These are the three subplots rendered. And how to access them? Access, AX, access them. Okay. So access.0, that is my first subplot. Its title, I need to set the text for its title. Earlier, what I used to do is plt.title and it has no other variations. So plt.title automatically sets the title for the graph. But here, as we are using access, this method of subplots, here the syntax to set the title is this title.setText, and again it takes a string data to render. Now, as I mentioned, you can transfer a variable name to that or a raw string to that. So I use the mixture of those profile for plus the name of the pulsar. Okay. So this will render my name of the pulsar as a title. Again, dot plot, as I had mentioned earlier, this plots a line curve. This takes a data. This takes a data and a color. It is similar to that. Now I will mention previously what I did. In the previous curve, what I did is just simple. PSR1 time, and I showed you it called complete list of time. Similarly, PSR1 data showed complete list of data. But now I am not plotting actually the complete data. I am plotting a part of it. Let's just show, I mean, let me show you why I am plotting this part and not the complete. Okay. So let's let's erase these indexings. I will explain this also. Don't be worried. Let's just plot for. I will just plot the. I mean this first axis AX0. That means I'll just run this without that index. Okay, that is accessing the complete data. So the complete data, that complete file, this file, its ith component, ith column has this. I mean, most of this, I mean, every column of that has this plotting. This is the complete profile, but you won't see this in any scientific papers. Like, you don't need this much, zero data or the noise. You are more required to study the pulse profile, right? This is not pulse, this is pulse. So that's why there are some manipulations, and in this case, the manipulation was that I did a slicing of the data. I didn't plot complete data. I did a slicing. Uh, as I mentioned earlier, this colon thing helps me slice any column or any array, right? So if I do something like 25 to 250, so what does this mean is that PSR2 time columns, 25th row to 250th row. That will be plotted. But for now, I will plot from the start. That is, if I don't mention anything from any one side of the column, that takes maximum value of it. Like if I don't mention anything to the left of the column, it will be go max to 0. Or if I can reverse it, like from starting from 150 to 250, and I don't mention something here, then it will end at the maximum. That is the end of the complete data. So you can play around with this. So if I'm just here only, right? AX0 dot plot. So I'm just plotting PSR to I for now. So if we run that, now I have just changed the indexing, that is sliced it to 0 to 250. So you can see it goes a pretty nice one, like it becomes a nice to see and visualize, right? Now you might be seeing there are more than one curve in this graph. That's uh, implemented using this. This is the main, I mean, helpful thing of matplot debugging. In the same axis, the same graph, you overplotted another data, and this time the data is Lin Paul. Okay, Lin Paul I haven't explained, I guess. Let's just ignore this for a while. What do you say? Okay, AX0 plot, PSR time, and PSR to V. This is the another column of the data, right? And this is the legend. Now, as I had mentioned earlier, legend, when you are using one plot, it will not come that much handy, but when we are using more than one plot, it will. So here it is given two plots, okay, and I have mentioned three names for legend. So it will read something like, okay, there is one plot, time and I. It will match it to this, the first integrated profile, okay, and it will legend it like the color of this graph is integrated profile. Then it will go to the second. It will find PSRB. It will map it to the second one, and it goes on like that. Okay. So if I don't, I mean, commented this variation and just mention these two, there will be, I mean, let's see, two graphs and two legends, linear polarization. This is actually wrong in legend terms. Why? Because when interpreted, it came to this and it understood, okay, this is the second plot I have to render, and this is the second legend I have to read. So it matched it, but it is actually wrong. Originally, what it was meant was this ax0 dot plot. This is another data. I just, let's assume that I arrived this lin Paul data from some manipulation of q and u. Okay, some manipulation of q and u, and still the same size as that column. So if I plot all these three, there are three plots, there are three legends. So what do you think will legend work as? Exactly, this will go chronologically. First graph, map to first, integrated profile. The red one, integrated profile. Red, how red? Color is equal to R. Then second one, linear polarization, because the second mentioned is linear polarization. Third one, PSR2V, it plotted this and mapped it to circular polarization. And that's how in one graph, you can plot more than one curves. And this is actually the pulsar profile you will be seeing more often if you have complete polarimetry data. Okay. Now, why use of subplots? This is the use of, this is one axis. Okay. This AX0, this complete thing is one graph. Now, using another graph. This is just a demonstration of how to use two graphs. Okay. I will be using again the linear and circular polarization data, more like integrated I data and V data and linear polarization data. You can see that, see this. AX0 had three curves. AX1, I set a title and I plotted one curve. Okay, nothing else. And AX2, another graph, but this time two plots. So I just wanted to demonstrate, if you have subplots, you can plot many curves in this. One had three curves, another had one curve, another has three curves, I mean two curves. So it is like this plot function is similar. You can just plot many, but if you have one graph, plt dot plot. If you have subplots, access the axis 0, 1, 2 indexed and plot. So after running that, you get these things, this type of graph. All this is rendered together. These three. Why three? Because I mentioned I have three subplots. First plot has three curves: red one, blue one, and the yellowish orange one. Let's say. And this one is second curve AX1, which I mentioned. This is AX1, and it plots PSR1 and PSRI and time. Okay. So this is actually the integrated profile, and this again is the polarization profile, and this is the third curve. It again has two. Now you see I haven't mentioned any legend, so it will not be mapping anything, but you can again check some legend here, I mean mention some legend here, and that's how you use, I mean, again, I am not demonstrating that, but you can also plot polarization angle in a graph like that just below this. No titles. Just below this, share the x-axis, and you will see, I mean, similarity to profiles you see in actual papers. Okay. Also, as I mentioned, I have used this. Share x is equal to true. What does that do? You cannot see any x-axis labeling, right? There is no ticker, there is no number. Why? Because all three curves are using same axis, and this is the axis. You can see no axis, no axis. Third one has an axis and a number, and this axis is actually shared by all of them. You can also do, I mean, this is the vertical one. You can do the horizontal one. You can share the y-axis and do the horizontal one. I am not showing that, but you can definitely explore that. That is also pretty much fun. So this was the basic of plotting of pulsar profiles. Mind you, this is the pulsar B 1929 plus 10. You can actually check that. What do we say? Let's check that. 1929, right?
Hmm. What happened? Uh, I am not getting the audio. Is it okay with everyone? I am not able to hear. Did we lose you for a while? I was wondering whether it was my network issue or yeah.
So my router got charged actually.
Mhm. Yes, yes. Okay, so we are
I
back.
don't know how much have you, I mean, put here.
There's one thing, Aniket. The thing is,
Yes,
we have
ma'am.
probably only about less than half an hour maybe left. So the reading of the fixed data, how much time it would take for us to go through that?
Ma'am,
Once
it's short.
you
It will be
explain
done.
about reading the fixed data and doing the baseline or other things, so that we again bring it up to where we are getting the data from EPN database, we can leave it at that because the rest you have discussed. What to do with
Yes, ma'am.
IQVIA, we have discussed in detail. So just
Yes,
reading
ma'am.
the fixed data and bringing it to this level. Okay, okay,
Yes,
let
ma'am.
me
Yes.
hand over.
Sorry for the disturbance. Okay, so you might have seen that we have actually achieved a pulse profile similar to what scientific papers do. So now let's go to another method of, I mean, another format of data which is very much prevalent these days in astronomy, and that is the FITS data format. So most of, as I mentioned, this European Pulsar Network database is actually a pretty old. Like it was created very long time ago, 98 or 95 types. And nowadays, the more of these pulsar observation data are in a format called PSR FITS. This is a specific pulsar FITS data format. For that, you let me explain what is FITS format. FITS is actually flexible image transport system. It is used to, I mean, transport image data of astronomical, I mean, telescopes. So the major thing is FITS is used for images, but here it will be used for pulsar and its data stream. Data stream is here basically intensity. Now there is a very peculiar structure of FITS format. Uh, I will upload this notebook also, and you can actually explore that. So I will just show you this. This is what PSR FITS structure looks like. Okay, major the FITS format structure is also similar. FITS format structure is what we call like a tabular structure. There is a data unit, a complete data unit, a block. It has a header and it has some data. Okay, that is the FITS format. Now PSR FITS format, which is specific to pulsars and which we will be studying here, that is something like this. There is a data header data unit, that is these are the blocks of data in PSR files. Okay, there are main header, history, some pulsar parameters, something like that. Now every header has some data, some information. So main header is also called primary data unit. So this header has relevant observer information, which telescope was used, etc., etc. So I will show you every kind of things as we move forward. So this is basically the data format where you have blocks of data structured one after another. Each block has a data header and a data. This constitutes a one block and then another block. Okay. So this is FITS format, basically used for images, where data header is for image information or the metadata, which what we call, and the actual data is the coded stream, that image data. Okay, so in PSR FITS files, this same structure is followed for pulsar intensity profiles. So here the data which I will be using is again from this paper, taken using Parkes radio telescope. I will also link that data set if you want to explore more. It is actually uh, also available in this DUI link. You can download it from there, but that will be very hectic. Again, more than 1,000 pulsars. Here I am using this particular research paper, 600 pulsars, to show you how to handle PSR FITS files. So these are the basic libraries which we will be requiring. OS is operating system, which you require, might not require, doesn't that much matters in astronomy. These NumPy, Pandas, Matplotlib, PyPlot, we have mentioned math. It is a basic maths module. SciPy, AstroPy, AstroPy IO.fits. This is the major thing for any fits file handling or reading fits files. Okay, this also actually helps in reading PSR fits because PSR fits is based on fits. I will mention everything as I move forward. Okay, so this is one of the methods of downloading data from your, what we say, Google Drive. This module helps you in downloading data from Google Drive, any kind of data, any kind of file, actually folder. Okay, so you can download it from there. I will show you this so that you know how to do that. So for that you need these modules, Google Auth, Google Drive, and these stuff, and you need the actual file, its sharing ID. Now, what is sharing ID? This. When you share any file, you have this type of link. Okay. So this part, this whole part, before view and after D, this whole code, this is all what we call file ID, and this is a method to download any data from file ID. Okay, so I'm gonna show you what else it requires. So once you run this is actually your authorization. You actually authorize Google Collaboratory to access your drive. So I will show you a sample like how to access. So this is my email, and I am accessing Google Drive using Google Collaboratory. This is actually the Google Cloud SDK module which is helping me doing that. So if you do that, you get this kind of code. And if you look closely, here it is enter verification code. This is the code actually you need to mention. Okay. When you run this, you get this link, you go to this link, authorize it, and you get this code. You enter this code here, and you, enter, press enter. That's it. You have authorized it. Now this is my file. Okay, this is my file name which I have in my Google Drive. So I will download that. So if I run this downloaded.get content file, it is actually downloading my data into my current directory. Okay. While it downloads, you can see that it is fixfiles.tar.gz. This is a compressed file. Okay, it is not like you will be able to open it. uh, it Okay, I will show you this thing later. So this is the tar gz file which you require. This is the compressed format of this is the compressed format. Okay, you can uncompress it in your system with any zip file opener. For now, this is the tar gz file. This is in my directory. Now how to open it? So for this is the required thing. This import JSON, shuttle, whatever you call it, zip file, tar file. These all are for handling compressed files. For now, I am not using any of these. I am using tar file. Okay. So using this, tar is my variable, tar file. Let's me open that. So what? How to open that? You copy this path. This is the path of this current directory. How to do that? Click on this three dots option. You can see copy path. Okay, you can do that. You can just paste it here. This is the copy path. Okay, they are under these columns, or you can just ignore this. If it is visible here in the root, just name the file. It will also work. Okay, and this is R. Mode to open the file. R is for reading. GZ is the compressed mode. That's why reading compressed mode. If you don't tell that, it will. By default, I think takes read, but there are other options too. Like you can write on that tar file, compressed file. So it is worth mentioning that you should mention R is equal to R GZ. Okay. Now this tar.get names. This is again from tar file library get names function. It obtains the names from the archive. You can see this. This is compressed. You cannot see what are the actual files in it, but this tar can read it. So I am extracting the names of the files inside this compressed file. This compressed file is how you download it from this database. This is the link to the DOI link which I mentioned. Here you can download actually. So the downloading will actually give it you this tar.gz file only. It will not give you direct images. Okay. So this is the code to actually extract the pulsar names. This is the list of pulsar data available. How do we achieve that? We achieve that using this D list. It got the names, and then I am splitting this. Maybe the file name is very much like abc.gz. You see now 2018 dot pulsar name. So I don't need complete path. I just need the pulsar name. So separated it using dot split method. Okay, why is it showing an error? Okay, I haven't Imported tar file. Oh, okay, this is what happens if you don't run the first cell. Okay, I haven't imported the tar file, and I'm trying to use the tar file, so this won't work, right? So now I have imported the tar file, so this will work. Okay, so now it works. So as I said, pulsar list gets the names from the D list, and it splits from dot. This list has complete all the file names. Now I want individual file names. So how do I do that? I do that using this d dot split function. And as you can see for D in D list, this is actually the iterable. So D list has a lot of names, and I take one, I split it from dot. Dot may be used for extension, which is actually the case here. I will show you the complete file name in a while. For now, this is how we split pulsar names. So you can see these are all the pulsars whose data is in this compressed file. Now let's check what is actually the complete. So yes, as I mentioned, this is the complete pulsar file name. How do I know that? I know that because I have seen this data. How does this data looks like? Okay, so you can see these are the data. This is the complete file name. How many dots are there? Dot is here, dot is here. If you split this file name from dots, there is pulsar name, this megahertz, and then file extension. We don't need that. We only need file name. So we extracted file name. Now I am selecting one pulsar from this complete compressed file. So for that I am using this. This is again a function here which is very much helpful in Colab. So I am using this J09014624 profile. I mean pulsar to plot it. So I will run it. I have selected the pulsar and the file name is this. Now I can read that file. So from here, this is where AstroPy works handy. AstroPy has this fits module which helps you read any fits file. In our case, it is PSR fits, that is pulsar fits. So that is also a fits file. So we can open it. And how to open? Again, remember this is a compressed file. You are not actually having a PSR fits dot PSR fits file here. You are not getting it. So how to read that? As I said, tar file can read that. So I had tar which has that file. Now tar.extract file. This will help me extracting that file. Earlier we extracted names. Now I am extracting the exact file, and it is taking the parameter p file. P file is this, the where is it? The pulsar name. P file is pulsar name plus dot 1400 dot psr bit. So this is the complete parameter. That is a file name. I gave it to tar.extract file. It extracted it, and then this hdul my variable. It read fits.open. That is, it read that extracted file as a fits file. So without this, let's remove this hdul.info for now. So if you run this, it has successfully extracted it. Okay. So how to check what it has extracted actually? So I will do hdul.info. This info gives me the basic structure of the fits file. Earlier I had shown you that fits file has these much HDU names and a lot of data, right? But in our particular case, in this observation, Parkes telescope observation, these are the HDUs, like data units, header data units, which are there: primary, history, pulsar parameters, band pass, and these things. Okay, there are all together 8, right? And you can see the types, and you can see that their dimensions. This dimensions is for the, I mean, type is primary. One is without which there is no fits. Okay, this is primary. The key. If you have any Excel data, there is one which cannot be empty or something. That is this primary HDU. And these are all binary tables. These all HDUs have some information and a table. So this dimension is for that table. Okay. So you get to visualize that there are some primary information and there are a lot of tables. Some has history information, some has parameters, some has data, and etc. etc. Okay. So here we are required to extract IQUV parameters to profile the pulse, right? So I will need that data. So these data is actually in PS, I mean PS parameter and subint. These two data headers are very much actually helpful for IQ/UV parameters and also other informations required to plot. Okay. Actually, subint actually has that IQ/UV data. That is the data stream complete, and HD, I mean pulsar parameter has informations, I guess, for data scaling and stuff. I will show you what all data it has. Let's just select those. Now again, HDUL. This is my fits file. It also accepts indexing. This time I am what I am indexing 012. What is to yes param. So this params variable has HDUL2, that is this header data event. This complete block of data is in params, and complete fifth block of data subint is in this variable. Okay, so if we do run that, that means my params has SDUL2, that is PSR param data. So now this function header, this is again in AstroPy. Okay, so this header helps you identify the headers in, what do we say, the that block, that data block. So you can these are basically the functions to visualize what all data are there in this. So you can see the it has information what extension it is, that is it is a binary table, and what all data it has. It is very much helpful in visualizing what we are working with. The main thing when main where we have IQUV data and its functions is in this subint. Now you can see subint is a very long data block, right? It has an extension binary table, that is it is a binary table, and it has a very number of, I mean number of things, number of columns, right? Uh, you can see, yeah, it has its binary table has one row and 20 columns. There are 20 such columns, these types of columns. And so this is what actually all the data of subint is, with its names. You can see offsets are there. There are location data, RA and TEC, that is right ascension and declination. These are the location data. All these data is in this data block of PSR fits. Okay, and some of the useful data which I can spot and which you should be spotting is these. Like you have cold type, it is saying IQUV, that is this data has polarization Stokes parameters, polarization parameters, and the data is according to that. It has T-bin. T-bin is time bin, that is the time per bin. If we observe a pulsar, how much, I mean what we say, minimum time value for which it is observed, and there are 1024 such bins. So that means you can actually get the information of time scale from this time bin and n bin. That is, there are 1024 bins, and per bin the value of time is this. So what should be the time scale? Okay, so this is what you can I mean visualize the data. Now coming to the more formal way. So this is subint.columns. If the data is binary table, it has got to have columns. So the columns can be accessed subint.columns, and it will help you identify those 20 columns which I mentioned earlier. So formats are also given. Units, if mentioned, that is right ascension and declination. These have to have units. So these are mentioned. So this is exactly sub data file, I mean data block, and this is its data, the table and its columns. Rows are its data, columns are its name. So you can see these are data weights, data offsets, and data actual data. Okay, so these things are what actually you require for IQUV parameter plotting. So how to access that? Again, as I have mentioned, this is again agreeing to that indexing pattern. So how to access this? Hmm, let's just access minus one is what for what? The last column here is data. Again, this is table row into column type. So only accessing one will give me columns, but accessing two, I mean two indexes will actually give me row into column, that type of thing. Okay, so if we access data as subint dot data 0 comma minus 1, that is uh, the last minus 1 एकदम, like from the previous what will you say, reverse indexing. So this data can be accessed how 0 comma minus 1. So if we check the data dot shape, this shape function helps me to visualize what actually the dimensions of it. It is mentioned 1024.14. I can guess this is IQUV data, 4 channels, and that is fine. But to ensure that I am accessing the correct data, I do that again, and I actually get this. As I mentioned earlier, Stokes parameters. What are these? This is basically how Stokes parameters manifest to actual polarization. Linear polarization can be given by root under q square plus u square. Actually, this is a printing mistake. I'm sorry for that. It is q square plus u square. Unpolarized light is q is equal to u is equal to v. If all those parameters are zero, that is an unpolarized light. So now we will extract the IQUV data from FITS files. So I have already extracted the complete data, that is 1024,1,4. What does that mean is there are 1024 rows, and there's a 4 channels, 4 columns, and there's a third in I mean, what do we say, dimension, let's just say, that is, if you are able to visualize it, it is 4 channels, and every channel has 1024 data, right? So now if parameter, what is it, IQUV again. So first channel is I. How to extract that data? Data's index 0. Index 0 is ith, right? I, then Q, then U, then there are 4 channels, 0, 1, 2, 3. So all these 4 channels can be extracted separately. 2 variables. Now what these variables will be? One will be I, the first channel, then Q, the second channel, then U, then V. And if you check the shape of all these files, I mean all these variables which we have extracted from the data is what? Data dimension has 4, 1, 1024, right? And if we extract it, now as you can see, it is 4. I mean, an array has 4, 1, and 1024 shape, but I am only mentioning one. So this is advantage of this Python language. It is automatically interpreting it as query me the 0th index and all the data possible in other dimension. That is, it is equivalent to say 0 comma all and all, that everything but the 0th column, something like that. Okay, so again, this shape function helps me visualize what I am actually extracting. Earlier it was 4 comma 1 comma 1024. Now I have taken 0th index out, that is of the shape 1001 comma 1024 q, and then so on. Okay, now the data offset. So PSR fits files stores these data not actually like a raw data. It has a offset is, you can see, like some data are 20, 10, 20, 30, 40, and it has a offset of 15. So if we subtract that, that will be my actual data. Okay, it is offsetted. I'm sure you have done these things in like measurements of any devices. There are offsets, zero errors, something like that. That should be offsetted. This is that. This data is again where subint dot data offsets. How to do get that? As I said, subint dot columns gives you columns, but subint dot data gives you the data of these columns. This is again AstroPy function. I will highly recommend to read FITS file handling from AstroPy. These all are functions used there. Subin.data, data offsets. So data offs. How do I know that data offs is a column there? Because I could see there is data offs. Okay. So I again extracted that data offset. I printed that. It gives me again an array, and this time array has 4 values. Again, I have 4 parameters IQUV, and this 4 arrays, I mean 4 elements, are offsets for respective channels parameters. You can see there are two square brackets, right? Generally we have one square brackets, but this happens because this is not a one-dimensional thing. Okay, let's see data dot shape. You can see data shape is 1 comma 4. That is one row, four columns. Okay, so this is not one dimension. This is two dimension, row and column two. That's why easiest way to identify how many dimensions are there in this array, to see this number of square brackets is equal to the dimension. It had it been three dimension, it will have three square brackets. uh, this is the concept of array. Actually, I would not dwell a lot into that, but basically this is the representation of numbers in Python, and you can definitely explore it a lot. It is a very vast thing you can do, but this is the basic thing: arrays, how to represent arrays. These are the representation of arrays in Python. So again, I extracted the data scale factor. As I said, the raw data is never stored in PSR sets because that is very storage inefficient, and we have to store a lot of data. So we do these things. We do these, what do we say, manipulations with the data. We have some data offsets, we have some data scale factors to make that efficient storage. So this is a Python function I wrote, which will actually help me in deriving a raw data. You see, the data which is actually like the actual observation. Now here I have all extracted data offset, data scalar, and those things. Okay, I have extracted all these things. You can see these are the things. You can do this individually also. Like you can take I and you can subtract it. I mean, multiply with it the data scalar, that is this scale factor, and then add data offset and get the raw data. This is basically what this function is actually doing. This is a raw data variable, and it is taking data scale factors 0 comma 0 index. That is, it is taking 0th index of the data scale. It has, you can see, 1 2 3 4 4 numbers. So 0th number, then it is data array is what my this array original data. This is this data array, and this is a function only, right? This is function which will return me the raw data. I will use this function. Why I am writing this as a function? Because I have more than one data to extract as a raw data. So I will just run this. This is a method. It won't give any error if you see that this function is not defined. This function is defined as a parameter here, so don't be worried about it. So now let's isolate these IQUV data. Okay, so I have again, now this is the use of that scaling function which I just defined. This is the scaling function. It takes data array, data scaling factor, and data offset. So and returns four variables: so raw data I, raw data Q, raw data U, raw data V. So I just define data I to UV and use the scaling function. Now these data are my raw data. Okay, I can actually, like, these are my polarimetry data which I intend to plot. So this is the technique which astronomers use. Sorry, which this is the technique we use to actually baseline the data. So what we you will actually be seeing is like, let me show. No, this thing is completely on zero. These are the yeah. Let's just assume that this is very scaled data. I mean baseline data. It starts with zero. Sometimes your observation data would be something like starting from 200 and plotting this curve, but it is not like scaled properly. So to do that, this is a function, and this is the basic technique to scale it, that we sort the data, actual unscaled and unscaled data which has not gone through this operation, and take the center part of it, mid slice of it, and subtracts its mean from the data. You see, like, it is basically doing a baseline, like subtracting the average of most part of the data. It actually Open for your exploration. I have used their 300 to 612. Remember, there are 1024. You can do that, anything, any indexing, and check what is the baseline. So
I
this
am
is my,
guessing, Aniket, I'm
yes, ma'am.
guessing that like you showed the curve, the plot earlier, right? If you can just take a
Yes,
look
ma'am.
at that. So when we are baselining, we are baselining where it is noise and not the pulse. And
Hmm.
so probably the data is given in such a way that at the center
Yes, ma'am.
it is not the pulse. So I mean
Yes, ma'am.
from the original observers, probably is this a standard way in which it is always given, so that you are sure that if you are at the center, you are in the noise part. Maybe I'm just guessing.
Yes, ma'am. The EPN data actually has already baselined it and actually
Hmm.
scaled it
Huh,
efficiently.
huh,
So if
huh.
we plot that, we actually get the actual curve.
Yes,
Uh,
yes, yes.
this is, mind you, again I am mentioning it. This data is very simplified. This EPN data is just I use for plotting. This is very simplified. The
Mhm.
real data is not like that. Okay, the real data has to go all through all these manipulations to reach something like that. Okay, to the students, this has to be mentioned. EPN data is very much simplified, which I use. There are other data also. So those data I just demonstrated plotting. Actual data has to go baselining,
Mm.
scaling, then I mean do all those stuff, then deriving the polarizations, and then we can profile that. Okay,
Yeah, and
and
even at
this,
that, we are still a step away from the, I mean, getting the data from the telescope and then
yes,
getting
yes.
the. So this is still relatively simplified data.
Yes, again,
What we are
original
getting from.
telescope data has a lot of noise. We
Yeah,
have to
so
clean
that is
that
another
signal.
step altogether. Yeah, so this is
Yeah,
we are going step by step. So this is.
yeah.
Thank
So
you.
this
Go
is
ahead.
okay. Sure, ma'am. So this is where it is baseline, which is I mean, ensuring that the graph has actual zero values and a proper plot. So this again, baseline is my function. I took data I that my as my parameter, and I got the corrected data. Okay. So this is converting the raw IQV data from baseline. I mean, this is prepared data. Now you can manipulate it for this is the actual parameter slope parameters. Now you can manipulate for any kind of polarization values you want. Okay. So again, this polarization angle, as you can see, as ma'am has also mentioned, U and Q, these two parameters can be used to derive polarization angle of the pulsar observation. Okay, so psi is equal to actually half of tan inverse of U and Q. So how to write that programmatically? So this can be done using many ways, but the most preferred one is this numpy. Again, numpy is always imported as NP, matplot is pyplot is always imported as PLT. These are some conventions, so you don't need to be worried about it. So what this does is polarization angle. This is my variable np dot degrees. Uh, let's just go from inside to out. Okay, so actually this is the most inside thing. There is nothing more bracketed here. Okay, this is data u corrected by data q corrected. That is u by q. This thing has been written here. Now I need to have this. Okay, and let me write along with you. Okay, so let's have whole angle as a variable. Now I need these angle as degrees. Okay, you can by default it gives I mean radians. You I convert it into degrees. So how to do that? So np dot degrees is a function which helps me do that. Now, what we have to convert? So we have to convert all this function, I mean, this mathematical operation into these. So how to write that? So 1 by 2 is obviously 0.5, and that is multiplied by the tan inverse. So how to write tan inverse is Python is using this function. Okay, there are function of tan inverse in math module also, but NumPy is more, I mean, streamlined to work with numbers and lists. So if you do np dot arctan, this is actually the tan inverse function of numpy, and now we need to define what we have to I mean find the tan inverse of. So we need to find the tan inverse of this complete thing. Data U corrected by data Q corrected. So I will enter this inside arctan. So what this basically is that I divided data U by data Q and then found its tan inverse, then multiplied it with by 0.5, that is 1 by 2, and then converted into degrees. Okay, so this is all what I have written. And don't be afraid that I have used third bracket here. It is just like for clarity that this is the expression, then this is the outer one, then this is, without it also mathematically it is correct. Okay, so don't be worried about it. So this is how polarization angle is calculated using the U and Q parameters. Now the dot max and dot min are the functions which help you define the maximum and minimum of any array. As you can see, polarization angle is also an array because it works on data U corrected, data Q corrected. These are arrays which have division. Again, arrays can have division, multiplication, square root, anything. Here it has tan inverse. So we find that maximum and minimum of the polarization angle. Okay, you can see what is the maximum and minimum. It is a quite symmetric almost, like it's 44 to minus 44 in degrees. Again, linear polarization similarly can be found how L is equal to under root of square of Q plus square of U. Again, NumPy again provides us functionalities to achieve that. NP dot square, NP dot square of data Q corrected, data U corrected, they are added, and whole thing is put under NP dot sqrt. This is the square root function of NumPy library. So this will give me linear polarization. So let's just calculate that also. So successfully done. So that means linear polarization has been calculated. Again, as it is already mentioned, V is the circular polarization, circular polarized component, and L is under root Q square plus U square. This is correction. I am again mentioning it. Q square plus U square is L, and angle is given. Polarization angle is given by tan inverse of U by Q. So all these things has been calculated by now, right? Now let's go to the plotting. That is very simple. Again, I will just, I know I have explained you plotting. I will just show you one thing, that is how to define the x-axis. Okay. So x-axis can be your phase. According to your phase, this is mostly used. Okay, I have not shown you the data. Okay, I will show you the, yeah, let's see one. You can see it is in basically x-axis always has angles, phases. So if you want phase, you can do this. This is what again creating an array, again useful by NumPy. NumPy dot arrange. Arrange gives us a start point, an end point, and what is the increment in between. Okay. So here I am using the time axis. You can use the phase axis also. Both are equally correct, and you can interchange between them. So how do I do that? I started with 0. The time axis starts with 0 for me, and I found the maximum. I know that there are number of bins I just mentioned previously, 1024, and I also had seen that T bin, that is time bin value, is given. So for according to that, my increment time value per bin is here, T bin, and starting point is 0, and there has to be 1024 parts, such parts. So how to calculate the end part? You can actually calculate that. You know the increment, you know the first term, and you know the number of terms, you know the last term. So this is just generating the x-axis for your graph. Remember previously our file had the time, complete data. This time it does not have that. It has some information. We can calculate time from that. So let's check what is the shape of time and phase. Okay, I have not run this, I guess. Okay, this is run. This is run. Okay, so now you can see the shape of time and phase. These are the arrays I created right now, from 0 to 0.44. With this increments, how many elements of time array are there? Time dot shape 1024. Okay, so I generated my x-axis. Now this is the sample plot. As I said, mainly plt dot plot is what plots your data, right? So this is what is actually plotting. Again, you can see I'm not plotting the complete data. I am plotting from 800 to end for both. And why is that? Because again, if I don't plot this, I just give time, and this you might be wondering why 0 is there. Data I corrected, remember the shape, it is 1 comma 1024. So I need to mention that its 0th index is what I require to plot. Oh, sorry. It is 0 and this is time. So this is the complete profile, but you can see this is pretty much unrequired. There is completely noise only. So with playing with that data, you can find where it is very visually suitable. So you can, what I found is from 800, you can see a pretty much visible graph. This is the data I corrected. That is the integrated profile, right? So plotting. I have just demonstrated plotting. PLT.figure, PLT.grid, then PLT.plot. All these plot are as one graph because I haven't used subplot. So in one graph, I have plotted three curves. What are three curves? Data I corrected, integrated profile, linear polarization, and the data V corrected. V is the circular polarization. So I have plotted all these from 840. That is my just found by where it is visually demonstrable. So if I plot that, you can see this is my pulse profile. This is my actual pulse profile for this data, this pulsar, right? Uh, Now, if I must mention, I haven't plotted the polarization angle right now, right? So, if I plot another PLT dot title, I have PLT dot scatter plot of polarization angle. You can see polarization angle has no, pattern as such.
Uh, yeah. If we kind of remove it wherever the linear polarization is not there, if you remove those scatter plots, there would some whatever is, see, we can make out that S shape there at the
Yeah,
center. I mean, under the pulse. So if you remove the other points, so that probably we leave it as an exercise for everyone to do. In fact, I also have to look at your
uh,
video several times and catch up with this.
no
Yes.
problem, ma'am.
Right.
I will just wind up. This is the last thing. Uh,
Hmm.
as I had demonstrated the use of subplots, so now I am actually using the subplots for plotting both polarization angle and polarization profile. Okay, as one graph. How to do that? I had just mentioned fig and axis. You see 0 and 1, 2 because PLT dot subplots has 2. Now here I have used another parameter grid spec.kw, right? This is what helps me defining the space each graph gonna take. If I don't mention it, what will happen is this graph and this graph both will be of same height. But you can see my polarization angle graph is height wise smaller as compared to my pulse profile graph, right? This was achieved because I mentioned 1 comma 3, that is 1 is to 3. So my first profile, first graph is 1, then my second one is 3 parts of that, like 1 is to 3 ratio is of this total height, right? So this is how we plot polarization profiles. First one is definitely this polarization profile, and second is this polarization angle. I have right now I have plotted everything from 840 to so on to the end. But what you can do is you can just slice it, or you can use another in this same plt dot scatter, let's say, and do another plotting. Like one is for 840 to something 870, let's say. I will just show you. This one is the thing you will, I mean, be seeing in actual research papers. So, mind you, they don't use matplotlib, but this can be done here also. Okay. So let's just say 840 to then 890 to 900. There are two plots. You can just assume, visualize this 890 to 900. Let's just change its color so that it is visible to us that yeah, we are plotting two. You can see there are two plots. Now I have just randomly chosen these indexes. These need not to be angle specific, but you can explore and play around with that, and you can make out this sweep. This is physically important observation. So this sweep is very much what we intend in these kind of pulsar profiles. Mind you, not every pulsar has this sweep. This pulsar which I chose has it, so you can visualize it. You can just find out this index where this sweep is only visible and this curve for this peak is visible, so that you can have a realistic plot. You can ignore this plt.plot. This is just to free my notebook that okay, I don't need these graphs anymore. So that was all for plotting. I am definitely skipping this polarization angle for particular point. You can do that. I will show you some of the pulsar profiles if you want. You can see, just for example, this is a pulsar profile. This is the integrated profile, linear polarization, circular polarization, and this is the angle sweep I am talking about. In my case, what is the angle sweep? You can see this is the angle sweep. So you can plot something which only mentions this. Okay. How to do that? Using that slicing option. Okay. You can do that. So this was how you actually plot it. And one more thing, you can see this pulse longitude, they have centered it to the 0 degree. I haven't, right? I have just used a phase scale. For me, it's
One might also
160.
look at L, no? One might look at L, and if L is below whatever, L is
Yeah.
noisy, then don't plot. That is another kind of a
Mm,
thing. But that could be left as an exercise to do.
definitely. Yes, ma'am.
And
Uh,
so we are kind of, you have been talking non-stop for more than 2 hours now, Aniket, but it was very
uh,
nice. This will be very useful for students who want to learn how to do this. And
Definitely, ma'am. They
you
can
had
now
pointed out the
explore the
comments. Huh,
database.
huh, huh.
They can you can
Yes, yes.
explore the database and see these are the PSR fits files. You can plot using this. That's what I have taught you right now. So explore these files, plot them, and match them with these curves. I will upload this notebook. Don't be worried. You can always ping me up. So don't need to be worried if you need any guidance.
If you
So
wouldn't
this
mind, after your exams, join the Telegram group, and then maybe you could share
I will
there.
join. I will join it right now, ma'am. It's no problem.
Mhm. Okay,
Okay.
we are kind of ready to maybe wrap up. Or was there anything you wanted to also point out here? Because any questions, etc., I will leave to Telegram group because we are overshot the time. And but you walked everyone through very patiently. I mean, also pointing out where one may go wrong and so on. So that way, it was very useful.
Oh, thank
Shall
you
we
so
wrap
much, ma'am.
up?
Actually, I
Shall,
know
huh?
how to like. I have been self-taught, so I know where people might go wrong and waste their
Yeah.
time exploring. So,
I'm going to go through very carefully all the steps you have pointed out because I have not yet succeeded in getting that. And one thing I should have mentioned right away before we started, perhaps, was that these two. The first step, of course, it is online accessible data, and I thought that maybe it is easier first to start with ASCII data. But the second part we are doing actually, we I got to know about it through as a part of an assignment um, in the Pulsar Astrophysics course being given by Ayuka, Professor Dipankar Bhattacharya, and I am also taking that course, and that is where I got to know. And I thought it will be nice if we have this step by step for any students who are. It's not necessary, of course, that all of you would be interested in pulsars only, but doing such a thing would be useful in. I mean, any of the other contexts also. So I saw that we had many more people initially, but not everyone may have had stayed on for this full I mean step by step process, but come back, look at it and record it, and then follow it through, code along with it. Thank you, Aniket, and thank you also Amritanshu for annotating from the chat. And
thank
so
you so much.
Aniket and Amritanshu, both of you, I mean I am thinking that perhaps we'll continue this. Every month I'm thinking maybe we'll have 3 days of code camp. The first day will be again starting from Hello World and very basic. Second and third day in different contexts.
Sure, ma'am.
So we
Sure.
will look on you as people we can depend upon, and more will join as we go along. We also had Saurabh helping us in the last month's one. So shall I stop the broadcast here now, or
Okay,
was
ma'am.
there anything you needed to say, Aniket? I think I'll stop the broadcast here and we'll continue the discussions in the group. Is that okay?
Okay, ma'am.
Yeah. Thank you so much, everybody, those who are
Thank you,
there, who
ma'am.
are
Thank you,
participating, and those
Amritanshu,
who
for
are
helping.